Okay, so in this video, we are looking at what we call connector problems, which are just applied problems using our minimum spanning trees that we learned in the previous video. So it says here, a connector problem uses a minimum spanning tree to find the least cost to link locations or objects. So imagine a question like this where we have 11 locations that require access to power. So they're all represented by these vertices on the network diagram, and the dashed lines on the network diagram represent possible cable connections between adjacent, so ones next to each other, locations. Now, imagine if you were on a really large scale, you wanted to connect power to all of these points, and you have to pay for this project. You want something that will be the least cost to you. So by drawing up a minimum spanning tree, you are able to make sure that each of these are connected in some way to another, and it's done so in the smallest possible way, using the smallest amount of resources so that it is the cheapest cost, right? We can look at this in terms of distance, in terms of cost, but there are a lot of real-world applications to what we are actually doing here. But in essence, we're just drawing minimum spanning trees and applying these to real-world problems. So we're going to go over everything that we've been doing, revise our minimum spanning trees, and look at how we would do this question here. Now, remembering with a minimum spanning tree, we are starting with a vertex, and we are connecting it to another one. Now, I'm going to pick this one over here, and I'm going to connect it up to here. Now, the reason I've done that is because it's the smallest or one of the smallest edges. So we know for a fact that an edge with the smallest weight will be on our minimum spanning tree. So now that I've connected these, there's a couple of ways I can go. I have 60 on this side and 60 on this side. I can pick either because they're the same. So I'm going to connect up this 60 here. Now from the edges that are from the vertices that are currently selected, we want to examine all of the weights of the edges, other edges connected to these. So I have 60, 70, 50, 40, 70. I'm going to connect 40. Now, once I get to here, I look and I can see, all right, we have 50 up here, 50 down here. Let's connect this one here. Now, here's where I'm going to pause in this section because now it's going back up to 70 and up to 60, right? So I want to connect maybe this one down here, but it makes the most sense to connect it to this vertex because that's got the smallest possible weight. And I'm just working my way around, right? I've just paused and started to go down here. You may pause here and then work up in this section or down here on your network diagram. There's a variety of different ways you can do this. But looking at this vertex here, I want to start connecting again here. I'm going to connect to this vertex because it has the smallest weighted edge. Now, I don't want to leave this one in the bottom right-hand corner out. I want to connect it, and there's kind of two other vertices I can connect it to. Either this one, which gives me a weighted edge of 50, or a weighted edge of 70. I want to pick the smaller one. So I'm connecting the weighted edge of 50. And now I go to this section of my network diagram. I want to connect this vertex down the bottom. I can either connect it to the edge with 70 or to the edge with 60. I'm going to pick the lower one. And now I want to make my way back up here. To connect this vertex, I can either connect to 70 or 60. I'm going to choose 60. And then I just connect this last vertex here. So I have my minimum spanning tree. Now, to find the length, I'm modeling how you would do this in an exam. We want to show our working out that we're adding all of these together. So I'm going to go 60 plus 40 plus 60 plus 50 plus 40. We're just showing the marker how we're getting the answer we have here. Because sometimes we can put it straight into our calculator and we can get the wrong answer. Sometimes we've drawn the wrong network diagram. We get the wrong answer. If we just give a bold answer, it limits the amount of marks we can get. So once we have this, we can write our final length, our minimum length is 510 meters. This way, we are going to get the cheapest possible way to connect all of these locations requiring access to power. So we're applying our minimum spanning trees to real world contexts. Now, our next example is saying that 7 towns on an island have been surveyed for transport and communication needs. The towns are labeled here and they form a network shown on the right. Now, here we have road distances marked in kilometers. Remember, it's important that we note the unit because the weighted edges just represent some quantity. It can be time, it can be distance. Now, we have to basically draw up a minimum spanning tree in part A that will ensure that all the towns are connected to the network, but that also minimizes the amount of cable used. So we're drawing a minimum spanning tree because we want to connect all of these vertices using a minimum possible distance between these towns. So we're going to begin, and looking at this, I'm going to pick a vertex to start off with. I'll pick vertex F, and I'll connect it to G. Why have I done that? Because 16 is the smallest number I can see. So I know for sure it's going to be on my network diagram somewhere. Okay, so from here, I'm going to inspect these two vertices and see which edge that kind of goes out from either of these vertices is the smallest possible one. And I can see I have an edge of 21 that goes from F out to D. I'm going to continue to inspect. I have 56, 33 to connect to E. I have 25, 28, 29, or 20 up here. So I'll connect to this 20 up here. Now, I'm just going to pause for a moment because I've started working my way left, but I don't want E to be left out here, okay? Because remember, I do need to connect to it somehow. So I can either connect it to D or I can connect it to F. I'm going to choose to connect it to F because the edge has a smaller weight. And now I'm going to continue making my way along this left-hand side. I only have 2 more vertices that I have to connect. I need A and C. But before I do anything, I need to inspect all the edges that I have connecting to my current vertices and see which one I can connect to A to C, which will result in the smallest possible sum of the weighted edges. So I can either connect C with 25, 28, 29, 32. 19 is the smallest possible number. It doesn't connect to C just yet, but it would be the smallest possible number to connect to A. And the reason I've done this is because now I can connect A to C because 18 is significantly smaller than all of these other ones. I had to connect to A eventually anyway, but I've done that first so that I can just work my way back and connect to C. I have my minimum spanning tree here with the smallest possible sum of the weighted edges. So it's saying just to draw the minimum spanning tree. I've drawn it on my diagram. In an exam, you'll be given space below to draw this one. Now it's saying, what is the minimum length of cable required? And this is essentially just asking us, it's saying that if backup links are not considered necessary, in other words, that means there are no loops in the cable network. So it's basically just asking us, what is the length of this minimum spanning tree? So we're going to say the minimum length is 18 plus 19 plus 20 plus 21 plus 16 plus 33. So I have all of these here. Now I just want to add them all up. So I'm going to take 18, add it to 19, add it to 20, add it to 21, add it to 16, add it to 33. And that gives us 127. And we look back at our unit in the question, it's in kilometers. So the minimum length of cable required would be 127 kilometers of cable. That brings us to the end of the video and looking at how we can apply the minimum spanning trees to some real world problems. Thank you so much for watching, and I'll see you next time.